In example 9.2.1, we're going to create a confidence interval for the difference of two population means to compare customer satisfaction levels of two competing cable television companies. 174 customers of Company 1 and 355 customers of Company 2 were randomly selected and were asked to rate their cable companies on a 5-point scale, with 1 being least satisfied and 5 being most satisfied. Survey results are summarized in the following table. I do need to make one correction to this. There was a typo. This is not x minus 1 and x minus 2. We need to correct these. 3.51 for Company 1. This is x1 bar, which is our sample mean. And for 3.24 for Company 2, this is x2 bar, our sample mean for Company 2. Construct a point estimate and a 99% confidence interval for mu1 minus mu2, the difference in average satisfaction levels of customers of the two companies as measured on this 5-point scale. So we'll start out with that point estimate. Anytime we want to find a point estimate of a population parameter, we use the sample statistics. So x1, 3.51 minus x2, 3.24. We subtract those in our calculator and we get 0.27. And so we can say that it seems that Company 1 is slightly higher than Company 2 on this satisfaction level by 0.27. But that single point, that's a single value. So what we like to do in statistics is not just rely on one single value, but create an interval of values that we feel confident about. So we'll create a confidence interval. We've got a 99% confidence interval, so that means alpha is 1 minus 99%. 1 minus 0.99 will give us 0.01. Some things that we need our error bound for the difference in the means. And since we're looking at large independent samples, and I say large looking at these n's, 174 and 355 are large. Because they are so large, we can use the normal distribution to estimate. So we can go back to z alpha over 2, square root s1 squared over n1 plus s2 squared over n2. So we'll need to calculate z alpha over 2. And we'll pull up a Google sheet. Google and Excel work very similarly here, but we're going back to that norm.s.inv so that we can figure out what our z alpha over 2 is. It needs a probability, so we're going to put in 1 minus, 1 minus 0.01, and that gets us 2.326, 2.33. Oh no, I forgot to split that in half. So norm.s.inv, we're doing a confidence interval. We always split alpha in half, so we're going to put a divide by 2 in there. Norm.s.inv, 1 minus 0.01 divided by 2, and that gives us the correct z value, 2.5758, which we would round to 2.576. And we can either do all of this calculation in Excel, or we can pull out our calculators, scientific calculator, and calculate it. I'm going to use the scientific calculator because I can keep it on my screen at the same time. But I'm going to write some stuff down so it'll disappear. 2.576 for my z, s1 0.51 squared over n1 174, and s2 0.52 squared over n2 355. So if I'm trying to use this in my scientific calculator, I'm going to make use of parentheses. Also, working in Excel or Google, we would still use a lot of parentheses to get this calculation. So starting up 2.576 times, big parentheses, we have to put all of this fraction in first for my calculator. Your calculator, you might be able to hit that square root button first and then type in the argument, but the Windows scientific calculator makes me do everything underneath that square root first and then hit the square root. So knowing how your calculator works is pretty important. So I will type in 0.51, oops, not square root, oh, come on, 2.576 times 0.51 squared divided by 174 plus 0.52 squared divided by 355, close the parentheses, and now I'm going to take the square root, and we can see right up here I've got 2.576 times the square root of the whole thing, square 0.51 divided by 174 plus square 0.52 divided by 355. And if I hit enter, I get 0.122. That's my error bound for this confidence interval. So we've got our point estimate, 0.27. We've got our error bound, 0.122. We can form our confidence interval. And I'll just put the general form up there so we can see what it looks like. x1 minus x2, that was 0.27. We'll keep the mu1 minus mu2 in there because that's showing us that we're doing the confidence interval. And then we will subtract and add. And since we're only dealing with 2 decimal places with the 0.27, we can make that error bound 0.12. And then we simplify this. 0.27 minus 0.12 will get me 0.15. And 0.27 plus 0.12 will get us 0.39. And then we can say that we are 99% confident that the difference in the population means is in this interval. Or we can say we are 99% confident the difference in average satisfaction levels of customers of the two companies is between 0.15 and 0.39. So there's our confidence interval. This confidence interval is pretty interesting in that the difference between these two means has to be a positive number according to this confidence interval. Well, we're 99% confident that the difference is positive. If the difference between two population means is positive, then it's very likely that these two means are very different in value. Saying that a different way, since our confidence interval does not contain 0, there's a very, very small chance that these averages are the same. If the averages are the same, then the difference would be 0. So that's kind of the frame of mind that we're going to be considering in this chapter when we're looking at comparing two populations. If we're looking at a confidence interval, does the confidence interval contain 0 or not? If it does contain 0, we cannot say that there's much significant difference between the two populations. If the confidence interval does not contain 0, like this one, we could say that the means have some significant difference.